All right, team, let's talk about gravitational potential energy, and let's relate gravitational potential energy to mass and height. But first, let's review potential energy, and let's remember that it means stored energy. So if you take a trampoline, you guys know that trampolines have all these like springs around the outside, and their surface is like this stretchy elastic surface. Right now, this trampoline, it has no energy or no potential energy, so it would have 0 joules, and that's because it's in a relaxed position. So it has no potential energy. But this one here, this guy has now jumped on it, and these springs are all stretched out now, and this stretchy material, it's being stretched, and it now has elastic potential energy and spring potential energy because of those springs. And that means that this trampoline is storing energy. It has the potential to move stuff. So it's going to move this guy in the upward direction. So remember that energy is the ability to move something or change its direction. And now this trampoline is sort of storing that energy, so it has potential. Okay, so we're going to mostly talk about gravitational potential energy, and that's the energy that an object has because of its height in a gravitational field. So that might sound overly complicated talking about gravitational fields, but it's really not. We all live on planet Earth, and in most physics scenarios, if you bring an object to a height, you actually are lifting it up inside of Earth's gravitational field, and so you have now given it some gravitational potential energy. So gravitational potential energy is the energy that an object has because of its height in a gravitational field. And let's notice again that if it's in a relaxed position like this, then it has no gravitational potential energy because it's not at, if anything has a height of 0 meters, then it has no gravitational potential energy. So let's think about the factors that affect gravitational potential energy. And the best way to see those factors or variables that affect gravitational potential energy is to see how it's related to things. So gravitational potential energy is directly proportional to the mass and the height of an object. We have a new relationship that we'll be studying, and that is this one. I'll write it in orange. GPE, let me do a little better handwriting. GPE equals mass times little g times h. And I want you to remember that little g, that's the acceleration due to gravity, and that's constant. That's 9.8 meters per second squared. So little g does not change unless you go to the moon, unless your gravitational field is a different gravitational field than Earth's, like you go to Mars or the moon or into outer space and you have none. Then you'd have no gravitational potential energy if you're in the vacuum of deep space. Anyways, let's look at a couple scenarios. So we have this 3-tiered diving board. Now, here's a given. I'm going to tell you guys that these 3 dudes, orange, purple, and green dude, they're clones. They have the same mass. So we're not going to change mass in this scenario, but we're going to look at how much gravitational potential energy they have according to their height. So they all have the same mass, and let's calculate their gravitational potential energy. So if let's see, he's green shorts. So we know that this guy is at a height of 3 meters, and we know its mass, and we certainly know that little g equals 9.8, and so all you got to do is calculate. I did not mean for that to rhyme, but it did. GPE equals mgh. Remember that if their 2 variables are just right next to each other, like you can see how these 2 variables are just right next to each other, it means that they're multiplied by one another. So GPE equals mass 34, what was it, 34 34.0, yep, 34.0 times 9.8 times this guy's height, which is 3 meters, and you calculate that this guy has a GPE of 1,000 joules. Okay, so just calculated the amount of energy that this guy has. He's got 1,000 joules of energy. Now let's do purple. Now there's a couple ways to do purple. One way is to do the same thing we just did. We know he's at a height of 6 meters, so we just plug in that. Or the quickest way is to notice that his height is twice as large as green shorts. And so if his height is twice as large, then he has twice the gravitational potential energy. Why? Because GPE is directly proportional to the mass and the height, which means if one variable doubles, the other variable also doubles. So we've doubled this guy's height, and so we know that its GPE will not be 1,000, but it will be 2,000, because 2,000 is double 1,000. That says 2,000 joules. So that's how you would calculate his height. And you could do it the same way. You could do it the other way as well, which is just multiply little g by his mass, 34, by the height, which is 6, 2,000 joules. Now, that's a great way to think about this and just thinking about the relationships. If one variable doubles, the other variable also doubles. That's a direct relationship. Now, let's look at this guy up here. This guy has a mass, or it's given to you. It tells you that his gravitational potential energy is 4,600 joules. So we know how many joules he has, and there's a question mark here regarding his height. So I want you guys to think, how can we solve for the height if we know the gravitational potential energy? And I want you guys in your notes to do that right here. So if you know that GPE equals mgh, and you know the GPE, and you know the mass, and you know little g, I want you to solve for the height. So go ahead and do that in your notes and see what you get for how high up he is. And you could round to like the nearest whole number. That would probably be helpful. Frankie, would you like to go outside? Be my guest. Okay. So let's talk a little bit about the directly proportional relationship, just so we have a deeper understanding and we can do a little bit more with that. So directly proportional, if one variable changes by a factor, the other variable changes by that same factor. And when we say changes by a factor, we mean that it is multiplied by a number. For example, if variable a and b are directly proportional, what's the new value of b? So we have a little bit of a math problem here. So what factor did variable a change by? So it looks like variable a started at 6 and ended at 4.2. So what's the factor? And factor means it's multiplied by a number. So 6.0 is multiplied by what number to get to 4.2? Now, if we do, you could just set this up just like a regular algebra equation, like 6.0x equals 4.2, and then you divide both sides by 6.0, and you would get x equals 0.7. So you'd find or discover that this little factor here is 0.7. So why is this important for physics? Because if one thing changes, the other thing also changes. That's a cause and effect, and we've been recognizing this pattern of a directly proportional relationship. So we would know that if variable a is changed by a factor of 0.7, then you'd know that variable b changes by a factor of 0.7. So 50 times 0.7 equals 50 times 0.7 equals 35. So that is how you would solve a question like that. So when you're thinking directly proportional, think, by what factor did my variable change by? If we know where it started and we know where it ended, then we could sort of find that. Okay, next thing. This one, if a object's height changes from 4.0 meters to 18.4 meters, how will its GPE change? So in this one, it gives you the starting height and the ending height. You know that it increases. We got to figure out by what factor does it increase. And you got to figure out how does the GPE then change. Well, recall the GPE relationship. GPE equals mgh. And you guys know that there is a direct relationship between GPE and height. So for whatever factor this number changes by times whatever factor this changes by, this one is going to change by that same factor. I want you guys to do this problem on your own and tell me what you get for the answer there, for what's the new GPE once the object's height is changed. I left out an important unit here. 50 joules of energy is what this guy would start with. Okay, so let's talk about potential energy and work. So a great way to think about potential energy is to think about how much work it would take to lift that object, because we're always putting objects at a height, and it's really easy for us to imagine that, oh, it takes energy to pick something up. So suppose you want to pick up a 40.0 kilogram block of ice to a height of 3 meters. It's a block of ice for a reason we'll talk about later, but I just needed an object that has some mass to it. How much work will it take? So let's recall that work is the amount of energy transfer. So how much work will it take? Well, we got to figure out how much energy then it's going to take to put it at that height. And remember that gravitational potential energy equals mass times g times height, and work equals force times distance. So those are some of the things that we have to remember when we're looking at a problem like this. So the easiest way to think about this is just how much gravitational potential energy does this block of ice have when it's up here at this height of 3 meters? Well, the block of ice has a mass of 40.8 kilograms, and you could just use your GPE equation. GPE equals mgh. Its mass is 40.0 kilograms times 9.8 times the height, which is 3.0 meters. And we end up with 1,200 joules. So let me just kind of move this over so I can have a little bit better handwriting and zoom in. So 1,200 joules. That's its gravitational potential energy. So super easy to calculate that. And that's the same, that it would take 1,200 joules of work to pick up this block and get it to that height. So by calculating the GPE, you've essentially just calculated how much work it takes to put it to that height. And a great way to think about this also is just recall that, if you had this ice block on the ground, if it has a mass of 40 kilograms, and you guys know that force due to gravity equals mass times little g, that's m and g. That's the m and the g of the mgh of our GPE. So that's almost all of it. So gravity exerts a force of 400 newtons on that block of ice. And if you can lift that up, if you can multiply that, if you can get that 400 Newton mass, if you can get that to a height of 3 meters, back 3 meters, then just think about it. Force times distance equals 1,200 joules. 400 times 3 is 1,200. And what is this force times distance dealy? That's work. So you can think about it in two different ways. You can think about it as the gravitational potential energy that the ice has up here, or you just think about how much force you got to exert on this object to push it to 3 meters. And in order to lift an object, you've got to be lifting it by its weight, which is its mass times little g. Cool. And I just wanted at the end to have you guys look at this simple machine. What's great about ramps, and this is why it's a block of ice, because now this guy can slide, this little dude can slide this block of ice up this ramp. And because we're at an angle here, it doesn't take 400 newtons to push this thing to get it to move. You don't have to lift something by its total weight when you're pushing it up a ramp. It'll just slide up a lot easier. You guys know this if you've ever like tried to just slide something up a ramp versus lifting it straight up. Of course, in this case, it has a frictionless surface. So you've got 200 newtons there. But in this case, you have to push it up longer. This is a hypotenuse. So you got to push it up 6 meters. You can't just lift it 3 meters. You got to slide it across a longer distance. And if you're going to calculate the work done, work equals force times distance, you get 200 times 6, which equals 200 times 6 equals 1,200 joules. The same amount. That's supposed to say 1,200 joules. Hopefully your handwriting is better than mine. Which is the same amount. So you can either lift the ice block up to that height or slide it up a ramp. Either way, you have got to achieve that GPE of 1,200 joules. And so think about the amount of energy it takes to get these objects to their respective heights. That's all for direct relationships, stored energy, and gravitational potential energy. Good luck, folks.